At this point, we know how to differentiate all polynomials, some rational functions, some radical functions, e to the x, and trigonometric functions, and any combination of those functions using addition, subtraction, multiplication, or division. So when we see a function that looks something like this, so let's say we have f of x with some polynomial on top here, and then multiplication of, let's say, e to the x and cosine of x. We now have all of the tools to tackle something like that. And that's a big deal. That takes care of a lot of the functions that you're ever going to see. There's a really important combination of functions, though, that we haven't seen yet, and that's composition. For instance, we don't know how to differentiate something like sine of x squared. We know how to differentiate sine and x squared, and if they were multiplied or divided, we wouldn't have any issues. The issue here is we put an x squared inside of the sine function. Similarly, if we had something like the cube root of a quadratic, let's say 7x to the fourth plus 6x squared, we don't have the tools for attacking something like that. And lastly, let's say we took e to the x and composed it with a cosine function. We don't have any tools for attacking that kind of function. Again, the difference between what we can do and what we haven't had the tools yet for is that we can add, subtract, multiply, or divide, but we can't put functions inside of other functions. Each of these three examples right here are composition of functions that we already know how to differentiate. In this video, we're going to introduce the chain rule. The chain rule allows us to use the differentiation rules that we've known previously and apply them to the composition of two or more functions. One of the sticking points for students when dealing with the chain rule is not really understanding the composition of functions. So in each of these cases, just real quick, what I'm going to do is identify each of these three expressions right here as the composition of functions. In this case, sine of x squared would be the composition, or f of g of x. If f of x was sine of x, this is what we call the outer function, and the inner function would be x squared, meaning you would put the x squared inside of the sine of x. In this second example right here, the outer function, or f of x, would be the cube root of x. The inner function is this polynomial here, 7x to the fourth plus 6x squared. In this last example right here, the outer function would be e to the x, and the inner function that we would put up in the independent variable there of e to the x would be the cosine of x. Each of these three examples right here are just the composition of two functions, though it's possible, and you'll often see the composition of three or more functions. All right, let's now step back, introduce the chain rule, talk about differentiating with respect to different variables, and then we'll come back and differentiate these three examples. All right, the chain rule says the derivative of the composition of f and g equals the derivative of f with respect to g of x. This is going to be for the first trickiest part for you, and we'll try to describe this pretty explicitly, times the derivative of g of x, which is the inner function right here. In Leibniz notation, we would write it like this. If we want to differentiate the function f with respect to x, what we first have to do is differentiate the function f with respect to g. This right here is exactly what this is saying. And then we multiply that by the derivative of the g, the inner function, with respect to x. This is a place where Leibniz notation is really valuable and can help you see why this is true. Why does this work? Well, when we look at these differentials, these are simply just fractional expressions. And if we were to cancel this factor of the differential of g between the numerator and denominator there, you would see that this would equal the df dx. All right, that was just the introduction of the technique. We'll now do a few examples with this. The one thing I want to do before we get an exact example is emphasize this move right here with what happens when you differentiate an expression with respect to another function or another expression. This point in calculus is a really crucial point. It can be difficult at first, but what we're going to start doing is differentiating with respect to different variables or different expressions. This is hugely powerful and exceptionally important. I want to introduce this with this example right here. What I have is y equals t squared times sine of x. I am now going to differentiate y with respect to t and respect to x. The main thing here is when I differentiate with respect to a variable in a multivariable equation, the stuff that does not contain the variable that I'm differentiating with respect to is treated as a constant. So in my first example here, I'm going to differentiate this with respect to t. This means I'm going to differentiate this, and I treat sine of x as a constant because it doesn't change as t changes. So this would be 2t sine of x. In exactly the same way, now if I differentiate y with respect to x, t is treated as a constant. So when I differentiate that, I'll get t squared cosine of x. Those two quick examples right there, while not having nothing to do with the chain rule, are extremely important. Again, what I'm doing here is if I'm differentiating y with respect to t, any expression in there or factor that has x in it is treated exactly the same as any constant I've done before. And when you differentiate with a constant, you can just move it out front or ignore it and differentiate around it. While these two examples have nothing to do with the chain rule, they're a really important concept at this point in calculus. When I differentiate y with respect to t, again, what I'm asking is how does y change as t changes? In that relationship, that has nothing to do with x, meaning I don't care about what's happening with any expression that has x in it. We treat it as a constant because the things that are changing are t and y. And in this case over here, the same but opposite is happening. Well, now if I differentiate y with respect to x, any expression that has a t in it is treated as a constant as it would normally. All right, this is the last little conversation we need to have before we can attack specific examples with the chain rule. In this case, what we're going to do, again, this is going to be a form of this move right here. We want to differentiate this expression, not respect to a variable like x. We're going to differentiate the cube root of 7x to the fifth plus 4x squared with respect to 7x to the fifth plus 4x squared. What this means is we're treating this expression right here as the variable, and we're going to differentiate around it. When I differentiate this expression with respect to the stuff on the inside, what happens is I differentiate the outer function, but this stays the same. First thing I'm going to do, as always you know, is I'm going to rewrite this cube root as a rational exponent. Importantly, when I do this, and what this means is I'm not treating this 7x to the fifth plus 4x squared as a variable or as an expression to differentiate. I'm going to differentiate around it. So in this case right here, as always with the power rule, I'm going to bring the 1/3 down, multiply it by the variable, or in this case, the thing I'm differentiating with respect to. And then I'm going to take 1 away to get negative 2/3. If this right here makes sense, and the previous example I just talked about makes sense, you're going to be in a really good place with the chain rule. All right, so let's get right into it here. So our first example here is f of x equals the sine of x squared. What we're going to do to differentiate this, we're going to differentiate the sine with respect to x squared and then multiply that by the derivative of x squared. It will look like this. So we first differentiate sine with respect to x squared. This gives us the cosine of x squared. We then need to multiply that by the derivative of x squared. And we know the derivative of x squared is simply 2x, which I would clean this up. F prime of x equals 2x cosine of x squared. Again, the idea, my first step is I differentiate this function with respect to this x squared, and then I multiply by the derivative of the x squared. All right, our second example is that one we played with a second ago. What we need to do now, again, is we're going to differentiate the outer function, which is the cube root, and then multiply that by the derivative of the inner function. All right, now when we differentiate, again, we had that same move we just did. We're going to differentiate with respect to the inner function here, this polynomial. We're going to differentiate the outer function of the 1/3 exponent. To do that, we bring down the 1/3 and multiply it by this stuff on the inside. Importantly to say here is, again, this stuff just stays exactly the same. We don't differentiate this stuff on the inside. It's as if in this case, that 7x to the fifth plus 4x squared is hanging out and watching around it as differentiate is happening. It's just hanging out as we differentiate around it. We differentiate this outer function. But then we multiply by the derivative of this inner function. So now we need to multiply this by the derivative of 7x to the fifth plus 4x squared. And we can differentiate that pretty easy with the power rule. We'll get 35x to the fourth plus 8x. Through a lot of examples that you'll have with the chain rule, there will be a question about then now simplifying. In my mind, generally, unless you have an application where there's going to be a reason to clean things up as much as possible, I often just keep it in its fully expanded form. Again, to review, what we did was we have this inner function inside the cube root. We don't do anything with that. We differentiate around it. Again, the cube root we wrote as the power of 1/3. We differentiate the power of 1/3, leaving the inner function, this inner polynomial alone. But after we differentiate it, we have to multiply by the derivative of that function, giving us this last factor right here times the result of the first differentiation. In this third example here, we're differentiating e raised to the cosine of x. Up to this point, you've probably noticed that any differentiating problem that involves e of x is a bit easier than every other function because e to the x, the derivative, is simply itself. Often though, when we get to the chain rule, e to the x starts to get kind of weird and a little bit more difficult. The thing is, nothing has changed with the derivative of e to the x. It just feels a bit different than other derivatives as we use it in the chain rule. First thing to understand is that e is the outside function, or f in this case, and the cosine of x is the inside function, or g of x. And that's because e is down here on the base level here, and the cosine is up in the exponent. There's no way that cosine could be considered the outside function when it's up inside the exponent. All right, to differentiate, the first thing we're going to do is we're going to differentiate e with respect to cosine of x. And again, when you differentiate this, e to the x, it doesn't do anything but output itself. So the derivative of e with respect to cosine of x in this case would be e to the cosine of x. Then we need to multiply by the derivative of the cosine of x. The derivative of the cosine of x is negative sine x. And now this kind of gives you an idea about the weirdness about e to the x when using the chain rule. And again, in this case, this term right here is the derivative of e with respect to the cosine of x in this case right here. And then this, the second factor, is the derivative of that exponent. What kind of feels strange, at least in my mind about when doing this, is the fact that we will always copy this e to the x factor down and then multiply by the derivative of whatever's in the exponent. So there you have it. There's an introduction to the chain rule. Again, the chain rule is a way of differentiating the composition of known functions. The chain rule is a really important concept in calculus. In fact, you're going to see very soon that with the chain rule, we can actually start differentiating things that aren't functions. Previously, we've only differentiated functions. Now with the chain rule, actually, we're going to be able to differentiate different equations that are actually not functions, like circles, for instance. If you're a normal person, you're going to struggle at first with the chain rule, but don't worry. It takes a lot of work and time. I suggest that you work on how you develop the notation, how you signify the outer and inner functions. Look at different examples, different techniques for this. If you're struggling in any way with the chain rule, it might be worth it to go back to a pre-calculus text or resource and look for the conversation of the composition of functions. Again, since the chain rule is dealing with the composition of functions, you really need to have a solid understanding of how to compose functions or how to decompose functions. The third and final thought is, be aware that what you're going to get in some cases is the composition of up to 3 or more functions, and you'll have to use the chain rule in connection with the product quotient rule and our other differentiation rules.